Once again, I'm Phil Harrigan. I'm the Vice President of the Los Angeles chapter of the California Society for Healthcare Engineering. And with us also is Brian Guerrero. You can see his smiling face on the screen there. He's the one with the hair. He's the secretary of our chapter. I believe Tom Peterson, our president, will be joining us later. He's going to try to stop in. Our educational presentation this morning is going to be from David Shirk on curbing energy costs with heat recovery chillers. We'll get to that shortly, but first, I would like to thank all of our gold and silver sponsors whose support for CSHE allows us to continue to be the conduit for professional growth in the operation of the built environment for healthcare in California. These are our gold sponsors, and these are our silver sponsors. Thank you so much for your continuing support. Now, let me get on to our main act here. David, do you want to share your screen and take over?
I'll do it. Thank you. Can you hear me all right?
Yes.
All right, Phil. So once I'm on a very small computer, I'm working remotely. I apologize for that. So once I open up my presentation, I won't see you all anymore. So if you need to tell me anything, for example, you can't hear me or you can't see me or whatever, I'll ask that you pipe in and just do that if you'd be so kind.
Okay, so you want to take questions during your presentation?
I'm okay with however you want to handle the narrative here. We can wait until after to take questions, or if anybody wants to come off mute and ask a question during the presentation, I have no problem with that either. I love to do these things live simply because it promotes that type of dialogue back and forth, I think, a little bit more readily perhaps than a webcast like this. But I'll leave it up to you guys. What do you like how do you like to run your show, Phil?
I think we could do the questions as we go along. That I think works a little bit better, closer to a normal in-person meeting.
I'm good with that. I'm okay with that. And I'll go ahead and take things off here. Can you see my full screen and my cover slide?
Yes.
All right. So I'll real quickly introduce myself. My name is Dave Shirk. I work for a company called GPS Air out of Charlotte, North Carolina. We are a manufacturer of needlepoint bipolar ionization. So we're air cleaning, right? We do air cleaning and we keep cooling coils free of microbial growth and all kinds of cool things with ionization in the air and in equipment. And people always say to me, well, why the heck are you talking about chillers? It's because, well, I've been around a long time and I've done other things in my career. I've worked for some of the largest manufacturers of HVAC equipment in the world. So I've sold chillers and air handlers, and I've done environmental control and just a broad array of things that I still enjoy doing. As well, I am an ASHRAE distinguished lecturer, which means I talk to chapters all over the world about various things, various topics, of which I have 6 or 7 specifically geared to healthcare. This happens to be one of them. Today's conversation will revolve around heat recovery chillers for healthcare. And one thing I do want to mention, which I'm excited about, and I mentioned in the chat that we had a little bit earlier, along with being an ASHRAE distinguished lecturer, I was just appointed by ASHE to be the committee chair for their Sustainability Leadership Task Force. That's just sustainability and decarbonization. So I'm excited to take that role. It's something I love doing. I've always been involved in energy efficiency and sustainability of HVAC systems and hospital facilities. So if I can work with your chapter moving forward, I would love to do that as well. Quickly, a plug for myself and CSHE as well. I will be speaking in September in Long Beach and October in Fairfield at your regional events, Northern and Southern California events. I'll be actually talking about the topic of operating room environmental control, temperature, relative humidity, and things like that. So if you're going to attend, please come up, say hello. If you're not, you're going to miss out. So, I hope you'll be there. Beth, I'm doing my best to drive attendance at the events, and I'm sure they're going to be wonderful. I'm excited to be there in person, and it's excited as well to meet you. Another thing I will say before I move forward on this is I have a tendency to kind of paint things with a broad brush when I give these presentations. I have to, because I only have so much time. So I will say things and you're going to go, well, that's kind of sort of not true, or that kind of sort of, could kind of lean this way in that direction. And I agree. There are caveats to everything. Feel free to interject with questions or comments, but I will paint a lot of things with a broad brush just to get the topic on the table for future discussion or for discussion later on in the presentation today. So with no further ado, I will begin. And I've been giving this presentation for several years now at the ASHRAE and ASHE level. I've been promoting heat recovery chillers for almost 40 years. And I'm going to tell you, it was kind of a hard gig in the past. I don't think it's going to be that hard moving forward. Quite honestly, this slide kind of tees up the conversations, starting most recently and probably into the unforeseeable future with regards to why you need to consider heat recovery chillers. And I probably could end the whole presentation with this slide and just say, see ya. And the point is simply this: you kind of sort of have to. We've got these mandates going on, and you guys are well aware of it in California. It's been going on for some time, but we're seeing it across the entire country now, where certain locales, certain cities, certain jurisdictions are just plain doing away with new fossil fuel natural gas hookups to buildings. And that simply means that buildings are sooner or later going to be driven to all electric. And that means that you need to do things within your facilities moving forward that promote that concept, right? I would suggest, this is just me personally, this is not an official stance of ASHRAE or ASHE, but I would suggest that any facility manager in an existing hospital, which is everyone that has their doors open today, if you're in a position to consider replacing a piece of fossil fuel equipment, you should probably think hard. You should probably think long. You should probably bring in a consultant that can help you perhaps weed through the issues that might be involved with replacing a fossil fuel piece of equipment with another fossil fuel piece of equipment, because the day may come, you may not have fossil fuel for that equipment. So heat recovery chillers play beautifully to that exact issue. And we're going to talk about that moving forward. I just happened to tee up this slide because it appeared most recently as one of the most recent cities, Washington, D.C., that have moved to ban natural gas in most new buildings throughout their jurisdictions as well. I read a couple of months ago, I believe the city of LA has done the same thing. No new fossil fuel hookups in LA. So I believe that probably would involve hospitals. I could be wrong, but my guess is if it doesn't, it will. And so moving forward, that's the conversation. It's not so much, should I do heat recovery? It's, I'm going to do heat recovery. Let's just figure out how. So this presentation, it needs a little bit of updating, but it plays to that. Let's move forward with it. Now, I'm teeing up this slide. This is an ASHRAE slide I use in my ASHRAE DL presentation, simply to promote their advanced energy design guide for large hospitals that you see on the left-hand side. And the idea, the concept behind this guide is it will take a large hospital, which ASHRAE considers to be 500,000 square feet or larger. And that's what I'm going to be talking about moving forward in this presentation when it comes to some of the numbers I'm going to show you, consumption, savings, that type of thing. But it applies to smaller hospitals as well. And if you're an ASHRAE member, you can go onto their website and you can download this for free. If you're not an ASHRAE member and you have a friend that is, maybe you can bootleg a copy. Don't tell anybody I told you that. This is a phenomenal guide. It's actually about 10 years old. And what I like about it is that it, while it does drive hospitals towards a 50% overall energy reduction, not just HVAC systems, but the whole hospital, the building construction, the glass, the lighting, everything is talked about in this guide. It's like a cookbook, though. You can go to sections. If you're thinking about doing a lighting replacement by climate zone, you can go into the section that relates specifically to what it is you're thinking of doing from an energy upgrade, and you can read about what ASHRAE suggests you do. It's kind of like a cookbook, and it's really cool, and it's got a lot of great information in it, and you don't have to take it from cover to cover, and do everything in there. You can just pick and choose what it is you want to look at, what you want to implement, and it gives some phenomenal guidelines on how to do it. So I suggest, if you haven't seen this, even though it's a little bit dated, you get a hold of it. Because let's be honest, moving forward with sustainability and decarbonization, the first thing we need to do is become more efficient at those fuels, utilities that we consume, whether it be electricity or natural gas. And this book goes a long way to helping you promote that within your hospital-specific facilities based on ASHRAE recommendations and guidance. Another self-promoting slide here for me. These are 3 ASHRAE journal articles that I've written in the past. I want to point your attention to the one on the far left, benchmarking building energy use. That's 4 or 5 years old. If you're an ASHRAE member, you can download it in archives. If you're not, at the end of this presentation, I'll have my email address. By all means, just reach out to me. I'll be happy to share it with you. But this talks specifically about benchmarking hospital energy consumption. And a lot of the information that I have in the slides moving forward came from that particular article that I wrote and a couple of others, which I'll share with you as well, should you reach out to me. That's all this slide really is intended to do, except now that I'm thinking about it, the one in the middle, hospital operating room, environmental control, will build off of the presentation that I'll be doing in September and October at your Northern and Southern California event. So I hope you'll attend that. So let's talk a little bit about hospital energy consumption. This happens to be information provided from the U.S. Energy Information Administration. This is a little bit dated. It goes back to 2012, but it hasn't changed all that much. And what it does is it breaks down the energy utilization intensity of the EUI of various vertical market segments, such as food service and hospitals, schools, offices, shopping centers, churches, all kinds of stuff, right? And by energy utilization or EUI intensity, what I'm talking about is a simple methodology, somewhat simple. I explain it in the ASHRAE article that I'll share with you, on how you as a facilities management professional can take your utility bills, your electric bills, and your gas bills, and you can convert the costs for utilities over a year's period into the BTUs consumed per electricity and gas consumption. And then you can divide that by the square footage of the facility and come up with your EUI, or the energy utilization intensity in BTUs per hour per 1,000 square feet. And that's where you start. And that's where we're going to begin this conversation with this chart that does exactly that. On the left-hand side of the chart, we list the various vertical market segments. And on the bottom, we list the total energy utilization intensity per 1,000 square feet for each of those specific vertical markets. Now, you'll notice at the very top, food service, right? That would be like fast food restaurants, your In-N-Out Burgers in California, my Whataburgers in Texas, right? Whatever. Huge, huge energy consumers. And if we read this chart to the right and follow it down to the bottom, we can see that, for example, fast food restaurant consumes, depending on the year, somewhere between 270,000 to 300,000 BTUs per year per square foot. That's a lot of energy, right? But guess what? Guess where we come in? And number 2 with a bullet, right? Right below that, inpatient healthcare. That's hospitals. And we can see that hospitals are anywhere between 230 and 250,000 BTUs per square foot of energy consumption per year. That's a ton of energy. We know that. We're paying the bills. You're paying the bills. You see all the stuff that's going on in your hospital that's consuming energy. We're going to talk about that a little bit. We're going to talk about how we can use heat recovery chillers to help reduce this energy consumption drastically. But if you look at some of these other vertical markets, for example, you can see an office on average is somewhere under 100,000 BTUs per square foot per year. So considerably less. We're double and then some, most of the other vertical markets that are listed here. So we most certainly, as healthcare professionals, as engineers, and as facility managers, and the vendors that support you, have a long way to go and a lot that we can do together to help curb these costs. If we look specifically at a large hospital and its electrical energy consumption and its gas energy consumption, and then we break down that consumption by process, it can help us in our minds determine where we want to spend our money to try to garner the most in energy savings if we are going to place that money in a position as an energy, efficiency endeavor. This is information that came from the ASHRAE HVAC Design Manual for Hospitals and Clinics. If you are an HVAC facilities manager or design professional and you do not have that manual, I highly recommend you jump onto the ASHRAE website and buy it. It is phenomenal. But what they did was they took a hospital or hospitals in various locations throughout the country. There's several regions. I think there's 5 or 6. There's a Western and a Northern and a Middle and a Southern and all this kind of stuff. And they went out and they actually polled these hospitals and got a hold of their energy consumption. And then they broke that energy consumption down by region and by process, so that if you're in that region, you can kind of get a feel for how much energy your hospital may be consuming and where it is consuming that energy. This happens to be done for the South Central United States, which basically they're polling in Houston, Texas, where I lived at the time that I wrote the article that this particular chart came from. And I'll share that with you, be happy to. The point is simply this: if we look at a 500,000 square foot hospital, and its average, for example, electrical energy consumption of about $2.84 per square foot, 500,000 square feet, that hospital will consume about $1.5 million in electrical energy. That's what the utility bill would read at the end of the year. And if we look at the various processes that are occurring within that hospital, we can see that, for example, lighting consumes about 14% of that total $1.5 million. And it has a number 4 ranking from a standpoint of its importance in reducing energy, or its consumption of energy, if you will. If we read down here to ventilation fans, we can see they consume about 24% of the energy for that large hospital in the south central part of the United States. It is your number 1 consumer of electricity, with space cooling being number 2 at about 17%. So if you're going to try to hone in on where you want to save energy and money, you may consider first looking at fans and then cooling, because they are the number 1 and number 2 consumers for this particular location. Now, I will tell you this before I move forward. These consumption numbers don't vary much at all, maybe 5% location to location. So what I'm telling you is that most hospitals consume energy in a similar fashion, regardless of where they're located in the country. Minneapolis, Florida, San Diego, Washington, D.C., they're all within about 5% of one another with regards to these process breakouts. So I'm painting with a broad brush here, but you can get a feel for where your hospitals in California probably lie. Now, let's take a look and focus on the right-hand side, natural gas or thermal energy consumption. Now, why am I going to focus on that? Well, number 1, that's what heat recovery chillers help replace. Number 2, gas is going away, so you got to figure out a way to get rid of all this off of the energy gas consumption part of your hospital facility, because you may not have gas to work with in the distant future, and most certainly in the near future. If you're building a hospital in one of the areas where they ban gas, it may not be available to you. You may be needing to go all electric. So when we look at the biggest consumers, the standpoint of a large hospital facility and its fossil fuel energy consumption, we can see that reheat is number 1. It consumes about 65% of the total $500,000 per year down here at the bottom that 500,000 square foot hospital would have to pay to the utility company, somewhere in that area, with space heating falling in a distant second, most certainly in second place at 15%. So between reheat and space heating, that's 75% of this hospital's fossil fuel energy consumption. Now, this hospital is located in Houston, Texas. It's hot there. You know, you don't need heating to heat the building from a standpoint of the winter months. You're using the heat for the processes within the hospital. Most certainly, reheat is a process that's independent of what's going on outside the building. I'll talk more about that in a slide or two. And space heating is a very relatively insignificant part, still 15% of that total overall consumption. If I was going to spend my money as a hospital on shoring up energy consumption from a standpoint of fossil fuel use, decarbonization, et cetera, I would spend my money reducing reheat and space heating. I think that makes sense. And that's what we'll talk about moving forward. I'll open it up real quick. If anybody has a question or comment and you want to make it at this point, come off mute. Feel free to do it. I'll give you about 5 seconds. If not, I'll move on. I'm moving on. Here we go. Let's talk about reheat, just to make sure we're all on the same page and everybody understands what it is and why it's such a consuming process in hospitals. Typically in hospitals, we like to have a little bit drier environment. We like to keep the relative humidities a little bit lower than what you might see in more traditional environments, maybe an office or a school. There's reasons for that. There's two good reasons that I know of. Number one, lower relative humidities have a tendency to help promote drier indoor environments, and that helps promote reductions in microbial growth, mold, fungus, mildew, etc., from occurring within the actual environment itself, right? The higher the humidity, the more the chance there might be for microbial growth to permeate and proliferate inside the building, inside HVAC systems, etc. But one of the most driving factors, believe it or not, is simply staff comfort. Particularly in operating rooms where you see doctors and staff heavily garbed, 2 or 3 layers of clothing, perhaps gloves, maybe double gloved, booties, hair nets, masks, and all kinds of stuff, depending on the intensity of the operation they're performing. They can get hot and they can sweat. And what we need to do in operating rooms particularly is promote lower relative humidities. And that lower relative humidity encompasses those doctors in a blanket that can allow the moisture from their skin to be absorbed through their clothing into the air. And it helps keep them cool. We know that when we evaporate sweat from our skin, that absorbs heat and is one of the ways that we as human beings stay comfortable inside built environments. But throughout hospitals as well, you have staff that are garbed, maybe not double garbed or triple garbed, but most certainly they're wearing specific clothing for their duties, and they're working hard, and they get hot and they sweat, and in lower relative humidity environments they're more comfortable. So what we do is we overcool the air in order to dehumidify it more deeply so that it can absorb that moisture. And when we overcool that air and deliver it back to the healthcare space at the high air exchanges that we have inside hospitals, for example, in an operating room, 20, 25 air changes per hour, if that air is so cold that it's distributed at those high air exchange rates, the space itself will be overcooled. It'll be dehumidified properly, but it'll be just too darn cold for staff to function. So what we have to do is take that deeply cooled and dehumidified air and drive it back to a temperature that is more conducive to comfort once it's delivered at those high air exchanges in the space. So for example, if we're cooling the air to 52 degrees, and I were to provide it to an operating room at 20 or 25 air changes per hour, that operating room would probably be 53, 54 degrees Fahrenheit, way too cold for docs. So what I have to do is heat it back up to perhaps 62 and then distribute it to the space, whether it be an operating room or not, at a temperature that promotes a space condition of maybe somewhere around 68 degrees Fahrenheit. And that's why reheat is such a big deal in hospitals. And that is why it is such a large energy consumer. When we are cooling, we are dehumidifying. When we are doing that and deeply cooling the air, we have to heat it back up to a temperature with reheat that allows it to be distributed so that the space remains comfortable. That is why hospitals consume 60 to 65% of their fossil fuel energy consumption for reheat within the space. And that most certainly is something that we need to work on as an industry, and most certainly something that heat recovery chillers can take a big bite out of. And we'll talk about that moving forward. Let's talk a little bit about cooling though. Let's talk a little bit about chillers, whether it be a heat recovery chiller or not. What is it that we put a chiller into the building for? Well, we put a chiller into the building to help maintain the space at comfortable conditions, because there are external and internal loads that provide heat to the space that if I didn't cool it, the space would become too hot, right? Some of those loads do occur from outside the building, although they're a relatively small portion of the overall cooling load of a hospital facility. But solar loads and ambient temperature gains, et cetera, that are driven through wall constructions and windows and roofs and skylights, et cetera, contribute to heating the indoor environment. But once inside the indoor environment, we have other things that are providing heat to the space, such as lighting. Hospitals are heavily lit facilities. They have to be. You have to see what's going on. People, right? People emit heat to the space, as well as in this particular drawing, they talk about miscellaneous equipment as being a computer monitor screen. We know in hospitals, everything that goes beep, 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 beep is consuming electricity, and emitting some type of an energy load to the space as a byproduct. There's all kinds of things inside that hospital that are internally driving a cooling load that the chiller needs to take care of. Now, let's stop and think for a minute just about two of them. Let's think about lights and miscellaneous equipment, the stuff that consumes electricity to run. I have to pay the utility company, first of all, to give me the electricity to run that equipment. Then I have to pay the utility company again to provide chilled water to the space to remove the heat that equipment has emitted to the space. And then I have to pay the utility company again to take that heat outside the building to a cooling tower and reject it to the outdoor environment. So I'm paying for that electricity 3 times. Its use as its intended process, my requirement to remove the heat from the space with a chiller, and then the requirement to get rid of that heat that I've garnered from the chiller through a cooling tower outdoors. It gets pretty expensive. As well, this heat is there. It's in the building. What if I could take that heat and instead of just rejecting it outside because it's not wanted inside, I could turn it around and use it inside to help heat the building? Genius. That's what we're going to be talking about. That's what heat recovery is all about. Let's take a look at a typical hospital facility, and let's talk about how we heat and cool a hospital. In the basement, of course. I don't know if you have basements in California. We do in certain areas of the country where I'm from. In the basement is typically where you will find the boiler. You may have steam boilers for process. You may have hot water boilers for certain loads. If you have a hot water boiler, it's heating water, it's sending it out to the space. It may be providing it to air handling units and fan coil units and terminal units, as well as other processes, maybe baths and therapy whirlpools, perhaps kitchens, perhaps laundries. There's all kinds of hot water energy consumers within a hospital that we provide hot water boilers to help handle from a load perspective. So you've got your boiler and it's running, and most of the time these processes are required 24 hours a day, 7 days a week. So these boilers are running all the time. Typically they're fossil fuel fired. As well, in that same basement, maybe in a different room, but maybe not, you're probably going to have some type of a chiller, probably going to be a chilled water system if it's a larger hospital. And that chiller sends cold water out to the air handling units and the fan coils and the terminal units to help absorb those loads that we talked about that need to be removed from the space to make the space comfortable. And this is a typical scenario that you'll see in most large hospitals. And this scenario occurs 24 hours a day, 7 days a week, 365 days a year. I typically always have some type of a heating load. I usually always have some type of a cooling load. And these systems can be working simultaneously, one on top of the other in combination to help maintain that hospital facility in a comfortable condition and to provide for its processes. But I'm missing something here that I talked about just a little bit ago, and that is simply that I have to take that heat that I have removed from the facility, from the space itself, through the chill water process. And I have to send that outside. And usually I'll send it up on the roof to a cooling tower, where that cooling tower then rejects that heat to the environment. So I have taken the heat from inside the building where it's not wanted, and I have taken it outside and rejected it to where it's not an issue of concern anymore. I take it from where I don't want it and I get rid of it outside, and it seems to work well. And it has served us well years and years and years. But I want you to emblazon this picture in your mind. I'm going to give you about 3 seconds to do that, because I'm going to show you a slide that's the same slide, only much more simplified. Okay, I'm going to give you 3 seconds to look at this, get it in your brain. 3, 2, 1. What if we were to take that heavily intensified, high energy consuming process and convert it over to something that looks more similar to this? Right? What's the difference? Take a look at this one. Take a look at this one. Now, I'm painting with a broad brush, but what I did here was I got rid of the cooling tower, and I took the heat that I had absorbed from inside the building to the chill water system, and I'm turning it around and I'm sending it right back into the building as hot water, because that's how chillers work, particularly centrifugals and large chill water systems, right? I turn the heat from the building into hot condenser water. I reject that condenser water outside. Well, let's make it a little bit hotter and let's turn it around. Let's put it inside the building and use it for good. I can take it from this to this. Now, I may not totally be able to get rid of cooling towers, and I may not totally be able to get rid of boilers, but I may, if it's done right, and I most certainly may be able to reduce cooling towers and boilers with this type of a process. And again, that's what I'll talk about moving forwards. Anybody got questions or comments on that? Good so far. Well, I'm assuming everybody's still there.
Yeah, we're still here.
Okay, perfect. Let's keep moving. So we're going to recover waste heat and return it to the building. But what we need to do is we need to identify specific facilities types that have what I'll call simultaneous heating and cooling. All right. I'm going to run a chiller to absorb a heat load from within the building. And I'm going to take that heat load and I'm going to turn it around and shove it back into the building where heating is required. To do that, I need to be both heating and cooling. Hospitals are beautiful facilities for that type of an application because as I mentioned, you have heating and cooling processes going on almost all the time, almost every single day, almost every single hour, if not every single hour of every day. This happens to be a picture of a chiller manufacturer that I worked for. And this picture several years ago. And what you'll notice interesting about their facility on this shoulder day of the year, I can't remember, I think it was September, October, November, something of that nature, is you will notice cooling tower plume on the left-hand side, and you will notice the boiler exhaust plume on the right-hand side. This is a manufacturing facility that was making chillers that was consuming both natural gas for heating the building and utilizing an electric cooler to cool the facility and reject the heat outside. Well, guess what we did? We identified those loads. This manufacturer also made heat recovery chillers, and we put in a heat recovery chiller that allowed us to take advantage of that simultaneous heating and cooling that facility experienced certain times of the year. And we saved that facility at the time about $300,000 in operational costs per year, reductions in both electricity and natural gas associated with reducing cooling tower use and reducing fossil fuel boiler use. To do that is relatively simple. I'm either going to make this sound way too simple or way too complex. I'm not sure which it is, but it isn't that hard to do. What you see in front of you is a chart. I have identified the cooling and heating loads for a make-believe hospital in Make-Believeville somewhere in the country. And you'll notice along the bottom, I'm looking at a 500,000 square foot hospital that would have a peak 2,500 ton cooling load and a peak 2,000 ton heating load. Now, why am I talking tons heating and tons cooling? It's simply to keep the metrics on the left-hand side on the y-axis similar. I just took the heating BTUs per hour that was required in the different bins, and I divided it by 12,000 and converted it to tons, so that we're going to be speaking in terms of tons, both heating and cooling. That's it. No black magic. Keeping it pretty simple. So on the left-hand side, I have the total tons of heating and cooling. Along the bottom of the chart, I have the month of the year starting in January and ending in December, so 12 months of consumption. The blue bars are the cooling loads. The red bars are the heating loads by month. Let's walk through this and see what we have to do to size a heat recovery chiller. First thing I need to do is determine where the peak heating loads occur. The peak heating loads in this particular facility occur in both January and December. That makes sense, right? It's the coldest outside. If there are external building loads, the boilers are running to help handle those. That would be the time of year when your boiler consumption would probably be its highest. And we see that it peaks at around 2,000 tons, January and December, and it falls off throughout the year to where in June and July it's at its lowest, and then it rises back up again during the shoulder months and towards the end of the year to another peak. I also have to identify the peak cooling load. Now we can see here the peak cooling loads has been identified at 2,500 tons occurring in June or July, somewhere in that amount of time. And you can see that, of course, from there, depending, that load is reduced when the outdoor air is cooler and the load of the building is less, right? I also then need to determine where my minimum heating loads are. We can see that falls at about 1,500 tons. Again, coinciding with the peak cooling loads, January or June or July, somewhere in that time frame of the year. And then I need to determine my minimum cooling loads. We can see the minimum cooling loads, as I mentioned, occur in January and December, somewhere at around 700 tons of minimum cooled water capacity for that chiller. So we can see that there are all year long, we have simultaneous heating and cooling loads occurring within that building. We just need to determine what size heat recovery chiller we want to apply to optimize energy savings and to reduce fossil fuel consumption. And that's what I'm going to show you moving forward. It can be pretty simple. I have identified a minimum cooling load, and at that minimum cooling load of 700 tons, you will notice if I look at every single month of the year, I also have a simultaneous heating load occurring. I am always heating, I am always cooling. I can make this pretty darn simple. I can put in a 700-ton heat recovery chiller in this particular facility, and on January 1st, I can turn it on, and I can let it run every single day, every single hour that entire year and never turn it off, and always be cooling, and always be heating, and always be reducing energy consumption, energy costs, greenhouse gas emissions, et cetera, right? I turn it on, I plug it in, and I equate it to having one of like a bank teller machine, you know, the ones you go to with the card and you get money out of. I equate that to sticking a bank, you know, money machine in the basement. It's just spitting out $20 bills every second. It's just saving tons of money, tons of energy. I'll show you exactly how much moving forward, but this is one very simple way to plug in a heat recovery chiller once I've identified the simultaneous heating and cooling loads, where they occur and where they're maxed and where they're minimized. Pretty simple, right? But as well, I could optimize it even more. If I wanted to, in this particular facility, I could put in 1 or 2 or 3 heat recovery chillers that total 2,500 tons in capacity. And I could take advantage of many, many, many more hours of simultaneous heating and cooling operation, everything that falls within the pink triangle here, right? All of those hours, all of those months, all of those loads, I have heating and cooling occurring. Now you'll notice on the left-hand side, right, there are times when I would not be running my chiller to meet the heating loads, and I would need some type of an auxiliary backup hot water system, maybe a fossil fuel boiler that's remaining, or maybe an electric boiler, or maybe, who knows, a heat pump, something of that nature. But for the most part, I can garner many, many, many more operational hours of simultaneous heating and cooling, depending on how I decide to apply the tonnage of heat recovery chillers that I put on this job. There also will be times of the year in this particular scenario where I'll have made more heat than I can use, so I'll have to have some type of a storage or rejection methodology in place. Maybe it's an existing cooling tower, and I just take excess heat that I've made that I can't use, and instead of putting it back in the building, I send it out to the cooling tower. I waste it, but it's a lot less waste than I had in the past, and this is a great way to garner considerably more reductions in fossil fuel consumption and garner significant energy savings as well. You don't have to do it that way. What's cool about heat recovery chillers is it doesn't really matter what the total load of the building is, what the max or the mins are. If I can plug a heat recovery chiller 20-ton or a 200-ton or a 300-ton into this specific application, I still got that teller machine down in the basement just spitting out $20 bills every second of every day, just maybe a little bit less than I would get with a larger chiller, sized more appropriately. But you get my point. It isn't that hard to do, and more than likely you can tuck a heat recovery chiller or 2 or 3 almost anywhere in that hospital facility because of the simultaneous operation of those loads. Now, one thing you might want to look at doing is try to convert as much steam use as you can to hot water. I'm sorry to any of the steam boiler people out there that might be sitting in the audience, but you know this is coming. In fact, ASHI tells us that roughly 25% of the steam that's produced at the boiler escapes the system before it even reaches the intended loads through leaks and inefficiencies, right? We need steam in hospitals. There are loads that most certainly require steam, but if you are heating your building with steam by chance, you most certainly want to consider trying to put that onto the hot water system and then take the heat recovery chiller to pull that load off of the boilers and use it more efficiently through the heat recovery process. Talk a little bit more about that moving forward as well. Desiccant dehumidification is another great way to reduce fossil fuel use. I'm not going to talk a lot about that here. I will talk a little bit more about it in both September and October when I'm at your regional events talking about operating room environmental control. But desiccants are a great way to garner incredibly low relative humidities and dew points, and done right, you can use recovered heat for the heat rejection portion of what's required in a desiccant system, and you can see 40–50% energy savings from a fossil fuel perspective, because for the most part, you can eliminate all the reheat that's required wherever these systems are applied. Amazing stuff. If you want more information, reach out to me. I'll be happy to tell you what I can about it. Now, plugging heat recovery chillers into a facility, whether it be an existing facility or a new facility, isn't necessarily all that difficult either. You just need to find the space. For example, I can plug it in anywhere in the building where I can tap into the return water system coming from the traditional chilled water system, right? So I could plug a heat recovery chiller in at point 1. I could take the return water that's coming back from the chilled water system and run it through a chiller that actually will take the return water and chill it even further. And what I will do is take the heat that I've absorbed in the chiller through cooling the return water, and I'll pump that heat at a higher elevated temperature and pressure and make hotter water, condenser water, and pump it into the hot water side of the system instead of sending it outside to the cooling tower, right? Or I could look at putting a standalone singular heat recovery chiller in the equipment room with the other traditional cooling only chillers that may be there as well. This could be, again, almost any size I want it to be. If I have in the application that I showed you earlier, I could put in a 100 or a 200 or a 300. This might be my 700-ton chiller that I turn on day 1 and let it run all year long and garner savings. That's another way of doing it. Or I mentioned perhaps 1, 2, or 3 larger heat recovery chillers, perhaps even sized to handle the entire load, understanding that there will be times I need to do something with excess heat or provide a little bit of heat that can't be garnered from the system, but that's something we most certainly can work around. So depending on what you want to do and how you want to do it, there are a multitude of ways that heat recovery chillers can be piped into both existing and new systems. You just need to think it through. Let's talk about the money, right? Show me the money. This is the important part. And I'm going to, again, paint this with a broad brush. And I'm going to say, from my simple mind, if I can save energy, I'm probably going to save money and utility costs. And if I'm going to save energy and money and utility costs, I'm probably reducing energy consumption to where I'm more sustainable. And I perhaps have reduced my greenhouse gas emissions as well. And that pretty much holds true. I think, you know, the biggest move we have to make as a vertical market segment in the healthcare industry is simply just keep optimizing our energy efficiency. Reducing energy consumption will go a long way in achieving the goals we need to achieve. Let's just take it one step at a time. So that's what I'm going to talk about here, kind of getting the best of everything out of a particular energy efficiency initiative, and that being this heat recovery chiller that we talked about. And it just so happens that at the time I put this presentation together, I decided I'm going to go to the place in the country that had the highest utility rates, and that at the time was California. I don't know if it still is. A lot going on in this world today, but at the time, I went to your a local electric utility website, and I pulled off an electrical consumption rate of around 12.74 cents per kilowatt hour for the city of Los Angeles. So that's what I'm going to use moving forward, just so you know. And then I took a look at your Pacific Gas and Electric Company average cost per therm for natural gas at the time, and that was running somewhere around almost 90 cents per therm or per 100,000 BTUs for natural gas. So again, those are the two metrics I'm going to use in utility costs moving forward. If these aren't right, it's okay. Don't worry about it. I'm going to show you a chart at the end that will allow you to take more current rates, regardless of what they are, regardless of where you are in California or in the country, and come up with the same savings results that I'm going to show you for this particular example that I have laid out here for you today. And what I did was I took a conventional chiller, a conventional 95% efficient hot water boiler and a conventional cooling tower for this particular 500,000 square foot hospital facility with a 2,500 ton maximum cooling load and a 2,000 ton maximum heating load. And I compared it to a 700 ton heat recovery chiller. From a standpoint of operational costs, it's pretty simple because remember, I'm applying the chiller at 700 tons. I'm turning it on, I'm letting it run, never going to shut it off. It's real simple. It's just a very simple calculation to allow you the end result. And that's the calculation I made here. So I took the approximate efficiency of a traditional centrifugal chiller, high efficiency chiller, and I took the load at 700 tons, and I took the number of operational days, convert that into the hours per year to come up with the kilowatt hours of energy consumption, and I multiplied that times the cost per kilowatt that I showed you earlier for Los Angeles at the time, and I came up with somewhere around $334,000 per year in electrical consumption to operate that 700 ton chiller. I then looked at my conventional 95% efficient hot water boiler with a COP of 0.95 and came up with the therms required, again, multiplying it by the operational hours times the cost per therm. And I came up with a cost of around $844,000 per year for those boilers to heat the building and do their part all year long. And then I looked at the cooling tower because, of course, I have to take the heat that I've rejected to the chill water system and I have to move it outside to the cooling tower and get rid of it. So at about 0.6 kW per ton, the number of hours per day and the total heat of rejection, I came up with a cost of energy consumption, electrical energy consumption for that cooling tower at about $54,000 per year. And this is just back of the napkin math. You can do it yourself. You can plug in any numbers that you want to come up with your own savings based on tonnage, et cetera. Then I took a look at the heat reclaim chiller. Now, you'll notice that the heat reclaim chiller has a higher kW per ton of energy consumption compared to the traditional chiller. And there's a good reason for that. I have to take the heat that I have removed from the building, and instead of using a compressor to elevate the rejection heat temperature up to say 95 degrees Fahrenheit, where I can send it out to the cooling tower and get rid of it, I have to elevate it to a slightly higher temperature, maybe 120 or 130 or 140 degrees. And to do that requires more lift, more energy on the compressor. So the compressor itself consumes a little bit more energy, but there's a huge payoff in doing this. And I'm going to show you what that payoff is in about a minute. And you'll notice that at 0.769 kW per ton, using the same math and the same utility rate, come up with a cost, that heat recovery chiller, at about $600,000 per year to both heat and cool the facility at that tonnage, right? Now, there's demand charges. Because I have an elevated lift or a little bit higher energy consumption, electrical energy consumption on the chiller itself, I'm going to pay demand charges on that. And at the time, I was using a $15 per kW demand charge for your area, for your neck of the woods, which would have meant it's going to cost me another $43,000 per year to operate that heat recovery chiller. So I need to combine these two numbers, the 600,000 and the 43,000. But when I do that, I come up with heat reclaim or heat recovery chiller savings of $587,000 per year. That's the difference between running conventional chillers and conventional boilers with cooling towers to running a heat recovery chiller, even with the extra demand charges, at 700 tons per year for that particular facility. Tremendous savings. There's a little bit more to this than meets the eye, right? Because guess what? If I can take that heat that I would have rejected to a cooling tower and I can bring it back inside the building and use it for good, I don't have to send it to the cooling tower. And cooling towers not only consume electricity, but they consume what? Water. And water ain't cheap, right? There's water costs involved. In fact, water is one of the highest rising utility rates, second to none. I think it's actually increasing, at least it was at the time, increasing faster than natural gas escalation rates were occurring. So water is a big deal. And at the time, your costs for water were somewhere around $4.42 per 100 cubic feet. In addition to water, I also have chemical costs because I have to treat the tower to keep it free of biological growth, right? And that on average runs somewhere about in the range of $3 per 1,000 gallons. So I have to take the cost for water per gallon and the cost of keeping the tower clean per gallon, and I need to come up with what the total costs for water are for that cooling tower. And when I do that over 8,760 hours at the cost of water in California at the time per gallon and the cost of chemicals per gallon, it's another $82,000 in savings I can add to the total savings of the heat recovery chiller. So at the end of the day, I take the electrical energy savings, I add on top of that cooling tower water and chemical savings, and I come up with a total yearly heat recovery chiller savings for a 700-ton heat recovery chiller and a hospital application of somewhere around $670,000 per year. Now, when you divide that into the tonnage of the chiller and you look at the savings per ton, you're looking at somewhere close to $1,000 per ton in energy savings for that heat recovery chiller. It does not take long to pay back the additional costs of a heat recovery chiller when you're saving $1,000 per ton year after year after year. It pays back like that. It truly can. Right. Here's the chart I promised, and feel free to take a picture of this if you'd like to. This is kind of nice. This is a chart that takes that same scenario that I just ran through and it breaks it down into other costs for utilities based on costs per kilowatt hour or cost per therm. Along the left-hand side, I list various costs per kilowatt hour. Along the top, I list various costs per therm, natural gas. So for example, we were at 12 cents kilowatt hour and about somewhere around 90 cents per therm. You can see that what I showed you, we're saving somewhere in this $640,000 to $735,000 cost per year for that 700-ton chiller. But if I had a different rate, if I was at 4 cents per kilowatt hour and $1.05 per therm, you can see the cost savings would be different, right? So based on those utility rates, you can come up with exactly what your cost savings might be if you've got different utility structures or you're working in different areas of the country. As well, remember, this is a 700-ton heat recovery chiller. What if I didn't have one that big? What if it was only going to be 350 tons? Well, I would just take these numbers and divide it by 2, and I'd come up with the approximate energy savings for a 350-ton heat recovery chiller. I could do a 100-ton, doesn't matter, divide it by 7, right? Or maybe I've got 1,400 tons in heat recovery chillers. I just take these numbers and multiply it 2. It's greater savings, but the dollars per ton savings are pretty much the same, regardless of the tonnage, the chassis size of chiller that you installed in your particular application, about $1,000 per ton based on LA energy costs at the time. It's considerable, right? Now, this is where I got to start updating things. You know, this was just kind of my end slide in the past. And I said, oh, by the way, you know, we can save the trees, we can save the whales. Everybody wants to do that, right? And yeah, you know. So I would show the equivalent greenhouse gas savings based on that singular 700-ton heat recovery chiller. But now this first slide and this slide are the only two I'm going to have to show. That's what it's all about moving forward. I hate to say it, but it is. I truly believe, and again, this is me talking, as chiller salespeople, if there's any in the audience, it's really going to be more about how much you can garner in greenhouse gas savings than it is the first cost of your equipment moving forward. I truly think we're evolving to that. But again, we need to keep in mind, anything we can do to reduce energy consumption, smaller equipment, right? Less first cost. We've got to do that as well. And we've got to try to convert fossil fuel loads, existing fossil fuel loads, over to electricity before they shut the pipe off, if that's what happens. I'm broad brushing. It may never happen, but we need to be prepared. And for example, this singular 700-ton heat recovery chiller would be the equivalent of taking 12,000 miles off of a road. If you had a car that drove 12 million miles a year, we've just taken that car off the road. Or for example, look at a couple others here if I can see them. It'd be the equivalent of, what have I got here? Planting, I know there was 5,897 acres of US forest, are the equivalent of removing 1,072 passenger vehicles off the highway every year. And you can convert that into equivalent CO2 savings per pound or per ton or whatever the case might be. We'll need to obviously justify that moving forward. I believe it'll be a part of our life cycle cost analysis, but I like looking at it from this perspective. It's a little bit more intuitive and understandable that this makes a significant impact when we do things like this. And heat recovery chillers are a great way to accomplish these kinds of energy reductions, these kind of energy cost savings, and these kind of greenhouse gas reductions and sustainability initiatives moving forward. This is an interesting article that appeared in the ASHRAE Journal several years ago. I know in California, you may be utilizing air side economizers in hospitals or medical office buildings. This particular article talked to the fact that when you are using a heat recovery chiller, it may be less expensive for you to turn off the economizer and turn the chiller on when it can garner heat and supply it back to the building, right? Less energy intensive and a lower cost in energy consumption to run a heat recovery chiller and turn off the economizer if you have a heat recovery chiller involved that could run, right? That's crazy, but it's true. This is an interesting article. And again, you've got to remember all the things you save. Water, you save on the cooling tower, may be able to downsize equipment. There's all kinds of things that can play into this that are important. And with that, I'll leave you with a quote from, again, usually I give this at ASHRAE presentations, but I still love this quote. It came from one of my favorite past ASHRAE presidents, Tim Wentz. If you remember, you may remember Tim, and he simply said that the largest challenge we face today is the failure to adapt to change. And I think that statement was as applicable at the time that he was ASHRAE president as it is today, as it will probably be 100 years from now. Change is coming, change is inevitable. We need to adapt and get ready. And hopefully this conversation helped. That's all I'm hoping. My email address is on there. Feel free to snap a picture of this or write it down if you want to, and reach out to me if there's anything I can do to help, or if you want the additional information that I offered to send to you on the side, just let me know and I'll be happy to do that. And with that, I will, I'm done. I'll turn it back over to Phil and questions or comments.
Okay, thank you very much, David. That was terrific. Does anyone have any questions for David? If we had more time, I'd quiz you on the problems of retrofitting these into existing structures. You know, space is at a premium, of course.
It is.
To bring these in, but the benefits are obvious. Now I'd like to move on to what were other species events coming up. Beth, can you go back to my screen? I think,
You'll have to reshare it, Phil.
Okay. Yeah, okay. Very good. Okay. We've got we've got a number of things coming up soon. Tomorrow, Orange County's got a chapter meeting tomorrow morning on humidifier design and maintenance. It's in person at Southland Industries in Garden Grove. And then a little later, San Diego chapter is having a golf tournament. We got a lot of golf tournaments coming up. See, she loves their golf. And tomorrow is the last day to sign up for the MEC exam that's coming up at the SoCal seminar on September 15th. The Central Valley is having a golf tournament on the 19th. Silicon Valley's got a chapter meeting. Oops. And then we've got a MEC study group. I'll talk a little bit more about MEC. I don't want to take too much more of your time, but we're having a couple more study groups for MEC. One on power plant and boilers on the 26th. And then we've got a webinar, Active Shooter Prevention and Response. That will be on the September 2nd. The second MEC, the last MEC study group will on HVAC and refrigeration systems on the 9th. And then on the 15th, the Southern California seminar in Long Beach. The 11th, we've got a golf tournament in the Inland Empire in Norco. Our next chapter meeting will be on the October 19th. We're skipping the September meeting because we've got that Southern California seminar. And then the Northern California seminar on the 20th of October, which is going to be the same information that's presented at the Southern California seminar. All these events, the details are available on the CSHE website. We're also looking for spaces to hold in-person meetings. So if you have a facility that will accommodate 50 people, we'd love you to get in touch with us. So either talk to Brian or Beth, and we could arrange to hold a meeting at your facility. That would be wonderful. Now, I wanted to talk briefly about MEC. That's the Mechanic Evaluation and Certification for Healthcare. MEC is the national certification for healthcare mechanics. To be a certified mechanic, you must have at least 2 years maintenance experience in a patient care facility. With 4 years experience, you could be certified as a as a senior mech. Now, the test will be given at the Southern California seminar. It's divided into 7 categories, and you can see there the number of questions for each category. The little patch or pin that which is mech-certification.org. Okay. And anything else we want to? No, we don't want to talk about that. How about a word from Calvin? Okay, it's getting late. I think that's all we've got for you. If anyone has any questions or comments, speak now. Can everyone hear me?
I just got one thing. This is Joe McLean with the UCI Medical Center. We just went through a survey to see about replacing the boilers and going with heat recovery chillers. And one of the things we found out, it takes an enormous footprint to install this equipment.
Yes.
In fact, it was so enormous that we couldn't do it because there's no place to put it.
I'll just comment real quickly if I can. I can't speak specifically to your application. Obviously, if you can remove boilers and chillers and they're in the same room, you can kind of economize on footprint. But if that's not the case, a lot of heat recovery chiller manufacturers make units as small as 20 tons and as large as near 1,000 tons. So depending on where you can plug them in and where you can fit them in, you don't necessarily have to go with one great big unit. You might consider a modular type heat recovery plant consisting of perhaps modules of 40 or 50 ton units that might be more manageable from a standpoint of their footprint and fitting them to the space. It's just something to consider. And remember, you don't have to go all out. Every little bit helps.
Oh, very good. Thank you, Dave. Well, that's all I've got for you today. Thank you all for coming at the next at the California Seminar Long Beach.